3, negative 4 feet 10.5 inches. That means it's going down from here to down. Minus always represents the opposite side. So it's coming down this far, and this is the pipe diameter. It's a 20-inch pipe, and the schedule wall thickness, you can call it, is 1 inch. This pipe is 1 inch thick, and this is just the melt tolerance stuff. How much the pipe going to corrode over the life of the plant? The corrosion is 1/8 of inch is going to corrode. So we have to be taking that into account so it can last 40 years. What's the design temperature? And what's that? The two different temperatures in here. And what's the minimum temperature? The minimum temperatures are sometimes due to the process conditions. Sometimes up north slope, they want to design everything inside the buildings to -20. And the minimum outside the building is -50. So this is client requirement due to the site conditions. So we will put all the temperatures here. So there will be 3 different loads we'll have. And this is the pressure, which is the design pressure. So that comes from the line list. So this information comes from the line list. And this comes from the line list and piping ISOs. And this will come from the material specs. Here is your pipe material. Here's a carbon steel pipe, it's a 106. So elastic modulus or elasticity is right here. It's automatically for you. When you put this in there, it automatically enters your this number here, elastic modulus. This will come automatically based on the material. It's already built into the software. So this is all the information you put here as for the pipe. Now we're trying to say, hey, is the pipe is rigid or is there an elbow? If there's an elbow, we'll check this. It's a bend. If it's an expansion joint, we'll click this one out. If it's a reducer, we'll click this out. Then it's going to ask you here, okay, what size are you going to now? What is the size of the reducer? We'll say, here we'll say 20 by 18. But in our case, we've shown a rigid. That means it's a straight pipe. It's not a pipe, it's a flange. The flange, the valves, these are considered rigid because they're not flexible. Anything which is not going to flex is called a rigid element. Your valves, your flanges, those are rigid. So in this case, it's a flange, obviously, or valve or whatever they have. Your material, and this one here, here's the restraint. See, that restraint means there's a support. There's a name for the pipe support, so you can call it restraint or a support, either way. So we're telling here, hey, this is a restraint in the system. What location? We say node 3. Node 3 has a restraint. And here's the built-in window here. We are telling in the y direction.
You don't have a spring there, like the restraint?
Here's the hanger. This is a spring. So if you want a spring, you click this one out. So it will ask you on the side the information regarding the spring.
Okay.
So all we're doing here is so easy. You just pick up the information, where, from what point to what point, what size, how long it is, what's the diameter, what the wall thickness, what the pressure, what's the temperature, and where the supports are. And if it's a spring hanger, we'll click this. If it's expansion joint, you will click this here. And then we go to the next sheet. It will go automatically. It's going to go you 3 number to start with. So if you got 4, 3, next you can keep adding the numbers. So you can capture the whole system in these elements or segments and complete the whole system. So this is called the input sheet here in the Caesar program. The next one, John. So see, this is built right into the system. This is Caesar program. This is all we made a one problem. We started with a compressor here. We started with a compressor here. We came all the way, all the PSVs here, all the air coolers here, and here. So this is the exchangers, columns, So what we did is building those little elements all into one problem. So we created our own whole system. And when you do that, now you can check where the stresses, how much the stresses are, how much the forces are on the equipment here, how much the force here, how much the force here, what the stresses are, and all these nozzles. So all the information you get out of one problem. And so all you're doing is inputting the sizes, and you don't have to repeat yourself. If the same size go on, you don't have to change it. It automatically carries the same information to the next sheet. The only time it's going to need changes if the pipe size changes, you want to change something different, then you can change that page, and from there it will carry the same till you want to change again. So it's very, it's easy to input the system here. This is what the stress engineers will get, and all the sports what we were showing, the restraints, they're all here, they're designated here. All these are the pipe sports. Okay. So this, and there will be node points here. Will show you another sketch where you can see the designation of every element. So this is the plot of that, and this is again an example of the portion of that. These are, we call the node points. So you're going from here to here. Because here there was a branch of pipe sport here, so you have to give an address because you want to show where the sport is. So you got to have its address. Same thing here. So all these pipe sports here, and these all have their unique number here.
So you give the plant force on the equipment, the changer vessel?
Yeah, what we do is here at the nozzles here, you call it an anchor there. So you will get all 6 degrees of restraints. You will get the forces there in north, south, east, west, vertical, and your moments. So those forces goes to the vessel group here, so they can qualify their connection here. So we can get all the forces on the structural, we can get the equipment, and we can check all the stress levels here. And this tells us the color here. If this is the color, the temperature here of the line in these portions, and this is the minus 20, the other brown one is all temperature is minus 20. You can check that way, which system is on what temperatures. Good. And this is a kind of small problem. It's a complete system. What we have is some kind of, let's say it's a tank here, and here are these 2 pumps. So we have connected all this together here the pipe supports down here, and we can run in there and get the forces here, here, and here, and at the locations, and we can check the stress levels here. So this is a small system, and these are the node points I was talking about. So see, every element, every time you have anything different than the pipe, if you got a sport, you got to give the dimension between the sports. Anytime you turn, you got to have a node point. Between the rigid members, you got to have a node point. At the flange, you got to, wherever you want to know something, forces and the stress levels, you put down the node points. And you can pick up any numbers. They don't have to be in sequence. You can design your own numbers and call out the way you want to. So that's all you got to do, learn is how to input. And once you input it, all the results are right there. Good. And now this shows the simulation of what happens with that temperature. See, if you want to see if your pipe is how it's growing, which direction it's growing. So this have that capability of, it will show you pipe was here, it moved this way. And it can give you a number how much it moved up here, how much it moved here, how much it moved here. So it can give you the movements everywhere you want to know. So this is again what we have here. It's the pumps here. That was the connection that's shown at the pumps here. There's a pump here, the piping here. We can calculate the forces, the stresses here. Go ahead. Okay, let's go ahead. Now, so this is the ISO we were talking about. This is how the ISOs we get. There's nothing on it. So we get it with the, it has the diameter, it tells the material. It shows what the diameter of the pipes are and what other elements are. They're all listed here for our input. So we have all the piping information right here. And this here is the information from the line summary from the process group. So now what we do is in the pipe stress, we put the node points here, the address is here. Go ahead on the next one. See this one right here. We started from, let's say, any place here. We put on the node points here to here, from here to here element, from here to there, and then you keep going all across, and you cover the whole configuration. And when you come from started here, you end up here, so you got a complete system here. And go ahead. And this is the line summary where we get that process information. This is how that looks like, a line summary. We get that information. This is PNIDs, same thing again from the process group to verify the piping, where it's coming, where it's going to. And this is again the input here, from, to, and the diameters of pipe pressure, then temperature. Here restraints at this node point, which is 6,000. We have an anchor. Here, this location, we have a restraint in the y direction. Yeah. And this is, we can see that after we input everything, we can look into this way, the complete pipe. You know, so that you can see it, it's exactly should look like the one your ISO is. If you have made a mistake, you coming from here to here, and you by chance you put a minus sign, this is not going to connect here. This portion is going to go that way. So you will know right away, wait a minute, that doesn't look like the way the system is supposed to be. So you can catch your own mistakes. Looking at this one, that will tell you, did you get the right input in there, the dimensions. And these are the load combinations part of the code we have to come up with. Because the combination of your primary, secondary, and occasional loads. So this is are the loads we tell the computer to calculate. So that software will calculate all these loads. Go ahead there. And this is the output when it's calculated everything. So it gives us this output window here. So now we can highlight whatever we want to see. Here's the displacement. We want to see anywhere in the system. We want to see how much the pipe is moving, what direction. Under any case, we go to deflections. Then you get the restraint summary. Any place you want to see the forces, you can see for any single load or the combinations. And then the stress levels here. So go ahead. Here is the load summary. We print out for those load cases. These are your thermal loads. This is the dead weight, and these are the seismic, earthquake, and wind. We give this sheet to structure group. So they can use this number to check the steel, and we give the same number to equipment group so they can check the nozzles and stuff. So we don't have to redo anything. We just print this out. This information is already on the drawing, so they know where that is. So this is the output for the forces. And this tells us the maximum stress for every case in the system. So we don't have to look at the whole system. There could be 10, 15 pages. Right at the top, it will tell you the highest stress. See, the highest stress in this case is 43%. That means we are way below 43%, and you can go up to 99%. So that tells you your system is adequate. You don't have to look further. You can just stop right there. You have the maximum stress in the system, you know. And these are the displacement I was talking about. Give you all those locations, all those node points, tell you how much they're moving in each direction and how much they are rotating. So you got this information. You got the forces, you got the stresses, and you got the rotations. And this is, again, seeing the motions of how much the pipe is moving. So you can look here, you guys look at this node point here. The line is moving 1.281 inches. Well, we can tell here, click it, hey, what's the maximum displacement? It will show this point is moving this much. So you don't have to worry, look in the chart. You can see right here the maximum. Now this is what is kind of entertaining stuff. You can see the simulation of how the pipes move under different kind of loadings. See, this is due to earthquake. See, if the pipe is moving so crazy, your natural frequencies are so low, you're going to know that, hey, this is not good. You want to put a guide here, somebody, so it doesn't do this fancy dancing back and forth. So you want to hold it there. We put a guide right here to stop that. Okay? So that's the motion. Now we're looking in the z direction, which is north-south direction. The previous one was east-west direction. See the pipe? It tells us when it's moving this way due to the earthquake, it's going to be doing this. So if the frequencies are 6, 7 hertz, or that range, it's okay. If you got 1 or 2, you know it's pretty loose pipe. You might have kind of put a guide. You're going to help the system to stay stable. So this kind of gives us a little feeling about the frequencies and the flexibility. Now this is due to the temperature. See this long headers here? When the pipe is growing, it's growing this way. When it's going to be cold, it's going to go back. So this exaggeration is going to be under thermal conditions operating. It's come this way, and when it's going to be cold, it's going to go back. So this will be the path of motion. So this is a kind of gives a pretty much idea about the output. You can check. You can see all these actions. It's pretty interesting. You can see from the side views. You can rotate it. You can move it. You can pan it. You can check it out your own work. That's the best thing about this whole thing. You don't need a checker. You can check your own work after you're done. You can see everything here, results, the failures. If there is anything above and beyond the codes, what you get is a red writing. Numbers comes red color. So you don't even have to worry seeing where it's failing. Everything is in black color or blue color, but wherever is failing, it comes a red flag, it's a red number, so you know where the problem is. So that's it's pretty much that one. Before we kind of split, I'll take a quick minute here, which is very important to check. I think you guys probably have seen it with other groups too, called the interface. You guys did you guys go through the interface deal? Okay. Well, interface is this kind of shown is here how the pipe stress group is involved with all the other disciplines. If we look at starting from the where is the client? Here's the architecture and client here. See, we get information and we need information from the client for the site conditions are concerned, what their requirements are, what they would like us to do, what they not like us to do. And then structure, we go back and forth. We provide them the loads, they provide us the steel. If they can't do it, we go back and forth. That's the interface, say, with structural. Project engineers, I know I don't have to explain that. They bug everybody all the time, back and forth, without doing much. So that's a lot of headache here, interface. This architecture is, we don't get too much involved with them, but on the north slope, because everything is built in the modules, pipes go through the walls. When the pipes are coming and going through the wall of the module, they want to know how much pipe is moving there, because they got to put the seals. You can't have a hole in the walls because it's going to be minus 50 degrees outside. You'll be losing all the heat inside the modules. So they had to have special design seals depending how big a hole they need and what kind of seal they got to use. Process equipment. And equipment folks, they need loads from us to qualify their equipment. Unless they have loads, they can't decide if it's going to be adequate or not. Mechanical process, same the line summary, we go back and forth, temperature, pressure and stuff there. Purchasing, we do the acquisitions to buy the special sports. We do the acquisitions and they buy it. And the piping design is mainly our main party we interface. Because all the design, they do it, we approve it, or we reject it. This is a constant interface there. Material engineering, this is where we get the specs of the materials. And if we want to deviate, if the piping material guys calculate the wall thickness, what the wall thickness has to be for the pipes, and sometimes they are too thin, because they design only based on the pressure in the line. But we have to design for the thermal, seismic, everything, keeping in mind. So sometimes we override, we request them to buy the thicker pipes. So that's the interface with the piping material. So that pretty much completes our circle. After that, what we do is to put all the books together with the calculations and send it to the client, and we are done and ready for the next job. So thank you for your patience. I know it was a kind of boring subject, but hey, some folks had to do it.